Hi friends, this is Naresh. This is my 11th lecture on mechanics of solids or strength of materials subject. Uh, this is common subject for second year B.Tech and second year diploma mechanical students. In this session, I am going to explain about important definitions and formulas used in first unit. That is simple stresses and simple strains topic. First of all, in this subject, types of loads, types of stresses, types of strains, those are very important in our subject point of view. That's why in this session I am repeating the fundamentals, that is fundamental definitions and formulas used in our mechanics of solid subject. Okay, first of all, I'm going to explain about types of loads. Okay, the types of loads are broadly classified. Loads are broadly classified into axial loads and shear loads or tangential loads, and third one is radial or bending loads. Okay, after that, axial loads again classified into tensile or pull loads, compressive or push loads. Okay, so these are the important types of loads. So tensile loads are pull loads, compressive loads are push loads, shear loads are tangential loads, radial or bending loads. So these four are important in our subject point of view. Axial load, axial load are thrust loads. If the loads are acting along the axis of the rotation of the member, okay, or along the axis of the object, okay, here you can observe here, this is the load acting along the axis of the object. Okay, so then this type of load is called axial load. Okay, so here the axis of the shaft and load both are in parallel. Okay, so this type of loads are called axial loads. So the examples for axial loads are tensile loads and compressive loads. Tensile or pull loads. When a body is subjected to equal and opposite forces acting away from the body, result increase in length is known as tensile or pull loads. Okay, here two equal and opposite pull loads. Okay, two equal and opposite pull loads are acting on the object. So these two are the equal and opposite pull loads. Okay, so these two loads are called tensile loads. Okay, so this is the front view, this is the isometric view of the shaft. Okay, so here this is a circular shaft, this is a rectangle or square shaft. Okay, now compressive or push loads. When a body is subjected to equal and opposite forces acting towards the body, result decrease in length is known as compressive loads or push loads. Here, these are the two equal and opposite push or compressive loads. Here, these two forces are acting towards the body. Okay, so like this. So these two loads are acting on the body. So it result, it causes compression takes place in the body. So these type of loads are called compressive loads. And second type of load is shear force or tangential force. When a body is subjected to two equal and opposite forces which are acting tangentially on any cross-sectional plane of the body, then the force is known as shear force or tangential force. Here you can observe here, this is the axis of the shaft. Tensile load or compressive loads, so both are acting along the axis of the shaft, but shear forces or tangential loads are on the surface acting on the surface of the body. So here you can observe here, this force just touches the outside surface of the body. It is not acting on the surface, just it touches the surface. Okay, so here this one also just touches the surface. Okay, it is not acting on the body. So these type of loads are called shear loads. Okay, when a body is subjected to equal and opposite forces which are acting tangentially on any cross sectional plane of the body, then the force is known as shear force. Okay, these two forces are tangential forces or shear force. These two forces just touches the surface, outside surface of the body. These two forces are not acting on the body. Okay, it is very important for shear force or tangential loads. Here you can observe here, this is the top surface of the rectangular bar. Okay, just this force touches the top surface. It is not acting on the surface. Okay, it is not acting on the top surface, just touches the surface. Okay, now radial load or normal load or bending load, this is the last type of load. So if the loads are acting perpendicular to the axis of the body, result in bending in the length is known as radial loads or normal loads or bending loads. Here you can observe here, push or pull loads, that is the tensile or compressive loads, both are acting along the axis, whereas the shear force or tangential forces are acting parallel to the surface. But these radial loads or normal loads or bending loads are acting perpendicular to the axis of the shaft. Okay, so these type of forces acting perpendicular to the axis. Okay, like this. So the angle between this load and axis is 90 degrees. So these type of loads are called radial load or bending loads or normal loads. Okay, here you can observe here, this angle is 90 degrees. So the angle between the axis of the body and load is 90 degrees. This type of loads are called radial loads. Okay, now I am going to discuss about types of stresses. The internal resistance force offered by the body against the deformation per unit cross-sectional area is called stress. Okay, so the internal resistance force offered by the body against the deformation per unit cross-sectional area is called stress. Okay, so here when you are applying tensile load, compressive load, or shear load, or bending loads acting on the body, then the internal resting force is offered by the body against the deformation. Okay, per unit cross sectional area. So the symbol of the stress is denoted by symbol sigma. Okay, this is the sigma. So this sigma is used for indicating the stress values. Okay, so the formula for stress equal to internal resistance force or external force. This is the external force F divided by cross section area. Here the cross section area of this shaft is in circular shape. So the formula is sigma equal to F by A. Direct load by area. Load by cross section area is the formula for stress. Now the units for stress, here the force, the denominator value is force, the units for force is newtons, and here denominator is area, the units for area is mm square or meter square. So F is in newtons and area in mm square or meter square or in centimeter square. Then the units for stress equal to Newton per meter square. It is in meters. Okay. Whereas if you are taking length in area in mms, then the formula is Newton per mm square. So these two are the units for stresses. But for large amount of stresses, we are indicating 1 mega in terms of megapascal, gigapascal, okay, kilopascal. So here pascal means it is also a unit of pressure. Here the units of pressure and stresses both are same. So the here this stress Newton per meter square, also called Pascal. Okay, 1 Pascal equal to 1 Newton per meter square. 1 kilo Pascal equal to 1 kilo. 1 kilo is the 10 power 3. So 10 power 3 Pascals. 1 Pascal is Newton per meter square. Similarly, 1 megapascal equal to 1 mega means 10 power 6. 10 power 6 Pascal equal to 1 Newton per meter square. Similarly, if you want to convert this meters into mms, then 1 megapascal equal to 10 power 6 by 10 power 6. Then okay, 1 meter square equal to 1 meter square equal to 1 by 10 power 6 mm square. So 10 power 6 and 10 power 6 both are cancelled. Then 1 megapascal 1 Newton per mm square. Okay. Now similarly 1 gigapascal equal to 1 giga means 10 power 9. 10 power 9 Newton per meter square. And if you want to convert this Newton per meter square into Newton per mm square, then you have to cancel 10 power 6. Uh, here 1 meter square equal to 1 by 10 power 6 mm square. So the 1 gigapascal equal to 10 power 3 Newton per mm square. Okay, these are the important units. Okay, units used for stresses. These all are units for stresses. Okay, now types of stresses. The stresses are broadly classified into normal stresses, shear stresses, and bending stresses. Here the bending stresses are formed by the bending loads. Shear or tangential stresses are formed by shear loads. Normal stresses are broadly classified into again tensile stresses and compressive stresses. These tensile stresses are formed by tensile loads or pull loads. These compressive stresses are formed by compressive loads or push loads. Okay, here tensile stresses, compressive stresses, shear stresses, bending stresses. These four are important in our subject point of view. Tensile stresses. The stresses induced in a body when subjected to two equal and opposite pull loads. Two equal and opposite pull loads. It is very important. Two equal and opposite pull loads are shown in figure like this. As a result of which there is an increase in length and decrease in lateral dimensions is known as tensile stress. Okay, so when you are applying a load, that is a two equal and opposite loads, then there is an increase in length and decrease in lateral dimensions is called tensile stress. Okay, so the formula definition is same, that is the load by cross section area, and symbol is also same. Here F is the force acting on the body, A is the cross section area. Here the positive sign, you have to consider positive sign for tensile stresses, because here when you are applying a tensile loads, then there is an increase in length. So you have to consider positive sign for tensile loads because it is in increase in shape. Okay. Similarly, for compressive stresses, the stress induced in a body when subjected to two equal and opposite push loads, as shown in here. Okay, these are the two equal and opposite pull loads. These two loads are acting on the body, Okay, as a result of which there is an decrease in length and increase in lateral dimensions is known as compressive stress. Okay, when you are applying two equal and opposite push loads are compressed loads, then there is an decrease in length and increase in lateral dimensions. So the stress induced in the load due to compressed loads is called compressive stresses. Okay, so the formula is same, but here you have to consider negative sign for compressive loads. So here negative sign for compressive loads. Okay, because when you are applying a compressive loads, then there is a decrease in length. So that's why you have to consider negative sign for compressive loads. Okay, now shear stresses. When the stress induced in a body when subjected to equal and opposite tangential or shear loads across the resting section results body tends to shear off across the section is known as shear stress. Okay, these two are the tangential forces. So the formula is shear load, that is F by resisting area. It is not a cross sectional area. Please observe carefully. Resisting area. It is not a cross-sectional area. Resisting area. You have to consider cross-sectional area of the resisting part. Okay. So it is different for tensile and compressive loads. Okay. So here symbol also different. For shear stresses, you have to consider tau. Tau is the symbol of shear stress. Okay. This is the tau. F is the load acting on the body. A is the resisting area. Okay. Here, here you can observe here, these two plates are joined by one rivet or bolts or nuts. Okay, when you are applying a load, when you are applying two equal and opposite loads on these two plates, then uh, this joining element may fail. Okay, may fail due to the playing of these two loads. So this element, this joining element is used to resist the loads. Okay, it avoids the separation of the two plates. Okay, so that's why you have to consider the resisting area of this this element. Don't consider the area of these plates. You have to consider this resisting element area. Okay, so here this is a resisting element. This is the example of a riveted joint. The stress induced in a body when subjected to bending loads is known as bending stress. Here you can observe here, this is a cantilever beam. When you are applying a load like this, that means this load is perpendicular to the axis of this object. Okay, when you are applying a load normal to the body, then it will undergo change in deformation by bending. Strain. When a body is subjected to some external force, there is some change of dimension of the body. The ratio of change in dimensions to the original dimensions of the body is known as the strain. So the symbol for strain is E epsilon or E. These two are the symbols for strain. So epsilon. Okay, these are pronounced by epsilon. Strain, here the strain has no units because the formula is change in dimension by original dimension. Here the both are numerator and denominator, both are dimensions, that is both are lengths. So the dimensions are same. So in numerator and denominator both are same units. So you have to cancel that units. So there is no units for strain. Okay, types of strains. Yeah, lateral strain, linear strain, tangential strain, compressive strain, shear strain, and volumetric strain. These six types are very important in our subject point of view. So I will explain one by one. Lateral or longitudinal, linear or longitudinal strain. So the ratio of change in length by original length of the body is called linear or longitudinal strain. Okay. when you are applying tensile or compressive loads, okay, when you are applying tensile or compressive loads on the body, then there is an increase or decrease in length. Okay, increase or decrease in length when you are applying two equal and opposite loads. Okay, so then where the change in length, the ratio of change in length to the original length of this body is called strain, linear or longitudinal strain. Okay, here when you are applying tensile loads, okay, the body may increase like this. So this increased length is called change in length, delta L. So this is the decrease in diameter. When you are applying two equal and opposite push loads, then the body may decrease in length. Okay, so this decrease or compressed length is called change in length. Okay, so here this is the increase in diameter, that is the change in diameter. Okay, these two are the examples for linear or longitudinal strain. Okay, so the formula is change in length by original length. Okay, here positive, you have to consider positive sign for tensile loads and negative sign for compressed loads. Okay, so because here when you are applying tensile loads, then there is an increase in length, so you have to consider positive sign for tensile loads. When you are applying compressed loads, the body undergoes sorry, the body may compress. Okay, so uh, there is a decrease in length, so you have to consider negative sign for compressed loads. Now lateral strain. The ratio of change in lateral dimensions to the original lateral dimensions of the body is known as lateral strain. So here I am considering same example as the previous one. When you are applying a tensile loads, two equal and opposite tensile loads, then there is an increase in length and decrease in diameter. Okay, this decrease in diameter is called lateral diameter, lateral dimension. So this is the lateral change in the lateral dimension, and this is the original dimension. So the ratio of change in diameter by original diameter is called lateral strain. Okay, here the diameter of the body is decreases, so you have to consider negative sign for tensile loads. Here, when you are applying two equal and opposite push loads or compress loads, then there is a decrease in length and increase in diameter. Okay, so here for in case of compressed loads, you have to consider positive sign for lateral strain. Okay, because here the lateral dimensions are increased and the linear dimensions are decreased. Okay, so the formula is lateral strain equal to change in lateral dimension by original lateral dimension. Here, for in case of shafts, you have to consider change in diameter by original diameter. Okay, here another example is there. In case of circular shafts, lateral strain equal to change in diameter by original diameter. But in case of rectangular sections or square section, then the lateral dimensions are width and thickness other than length. Other than, you have to consider other than length dimensions. So here width and thickness, these two are the lateral dimensions. So change in width by original width is called lateral strain, and change in thickness by original thickness also called lateral strain. Okay. Okay, these three are the lateral strains. Okay, you have to consider change in diameter by original diameter for circular shafts, change in width by original width, change in thickness by original thickness. These two are for this type of cross sections. Okay, now tensile strain. The strain produced by the tensile stress is known as a tensile strain. Okay, there is no units for strains. Here in tensile strains, we are applying tensile loads, two equal and opposite tensile loads. The formula is the same as the linear strain. Okay, this is the lateral strain. Okay, negative sign here. when you are applying two equal and opposite full loads, then increase in length. So you have to consider positive sign for linear strain, and decrease in diameter. So you have to consider negative sign for change in diameter by original diameter. Compressive strain. The strain produced by compressive stresses is known as compressive strain. In this case, you have to apply two equal and opposite compressive loads. When you are applying two equal and opposite compressive loads, then there is a decrease in length. Okay, decrease in length and increase in diameter. So here delta L by L minus delta L by L for linear strain. Here the length, when you are applying to equal and opposite push loads, then there is a decrease in length. So decrease in length, so you have to consider negative sign because it compresses the body. So negative sign for linear strain, and positive sign for lateral strain. Here the diameter of the body increases. Okay, when you are applying two equal and opposite push loads, there is increase in diameter. Okay, so you have to consider positive sign for lateral strain. Okay, now shear strain. The strain produced by shear stress is known as shear strain. Okay, this is the example. When you are applying two equal and opposite tangential forces on the body, this is the initial position of the body. When you are applying two loads in opposite direction, tangential force, then this is the final shape of the body. Okay, so this dark color indicates original position. This dotted line indicates deformed shape. Okay, so this is the original shape. This is the deformed shape. Okay, here the angle between initial position and the original position is called angular strain. This is the angular strain. This is the linear strain. Okay, volumetric strain. The ratio of change in volume to the original volume of the body is known as volumetric strain. So here this is the example. This is a volume. Okay, when you are applying different loads, mutually perpendicular loads acting on the body, then there is increase or decrease in body. Okay, there is an increase or decrease in volume. Okay, the ratio of decrease or increase in volume or deformed volume divided by original volume is called volumetric strain. Okay, the ratio of change in volume by original volume is called volumetric strain. So here you have to consider positive sign for tensile, positive sign for extension. Okay, increase in length, increase in volume, whereas negative sign for decrease in volume. Okay, V is the original volume, delta V is the change in volume. Now these are the important for our problems. These are the cross-sectional areas for different shapes. This is a solid circular shaft. This is the cross section. Okay, here the area for this circular section is here. Area A equal to pi by 4 d square is the formula for circular cross section. Okay, d is the outside diameter. So pi by 4 d square is the area for solid circle. Okay, in terms of radius, area equal to pi r square. Okay, this is a hollow circular cross section or hollow pipe. Okay, or hollow shaft. This hollow shaft having two circles, one circle outside circle having solid and inside circle having hollow. Okay, the formula for cross sectional area for solid, so solid shaft equal to pi by 4 d square, whereas uh, cross sectional area for hollow shaft equal to pi by 4 d square for outside circle and minus pi by 4 d square for the inside circle. Here inside circle is a hollow portion, so you have to subtract this hollow portion from the outside solid portion. So that's why I am considering negative sign. Okay, you have to subtract this inside circle because this one is hollow. Okay, that's why you have to subtract from solid. So this is the formula for hollow shaft. Now this is the another formula for triangle. This is a triangle. Okay, this cross section is looks like here. So here height h is the height of the triangle, b is the base of the triangle. So the cross sectional area of the triangle is equal to half into base into height. Okay, this is the formula for cross sectional area of the triangle. The area of triangle is for isosceles, for equilateral triangle or right angle triangles. The area of any type of triangle is same. That is a half into base height. Okay. Now this is the shape of a square section. Okay, this is a square bar. So the width and height both are equal for a square section. So all sides are equal. So here I consider length equal to b and height equal to b. So the area of the square section, area equal to base into height. So b into b, that is b square. Side into side equal, side square is the formula, area formula for square sections. Okay, similarly for rectangular sections also same. Okay, now I am going to explain about Poisson's ratio. Poisson's ratio is the ratio of lateral strain by linear strain. Lateral strain means change in lateral dimensions by original dimension, original divided by change in length by original length. Okay, this is the formula for Poisson's ratio. Poisson's ratio is denoted by symbol mu or 1 by m. Okay, these two are the symbols for Poisson's ratio. Okay, lateral strain by linear strain. In case of circular cross sections, delta d by d is the lateral strain. Delta change in width by original width is for rectangle or square sections. Okay. Here, Poisson's ratio also has no units. No units because numerator and denominator both are strains. Okay, strain has no units. That's why Poisson's ratio also having no units. Hooke's law. It is very important for engineering materials. Hooke's law. Within the elastic limit, the stress is directly proportional strain. Okay, this is a Hooke's law. So according to Hooke's law, the stress is directly proportional strain within the elastic limit. So the stress is directly proportional strain. This is the Hooke's law. Okay, stress sigma and epsilon is the strain. Now, types of moduli. Types of moduli are types of elastic constants. First one is the Young's modulus or modulus of elasticity. It is denoted by symbol capital E. And second one is the shear modulus or modulus of rigidity. It is denoted by symbol C or G or N. Okay. Third one is the bulk modulus. It is denoted by symbol K. Okay. These three are the elastic constants, and the units for these three are same as stresses. Okay. So the units for Young's modulus, shear modulus, bulk modulus, these three are same as stresses. Okay. Now, Young's modulus within the elastic limit, linear stress is directly proportional to linear strain. That constant is called Young's modulus. Okay. According to Hooke's law, linear stress is directly proportional to linear strain. Then sigma is directly proportional strain. So here sigma divided by epsilon is equal to constant. This is the proportionality constant. So this constant is called Young's modulus. Okay. So here Young's modulus is denoted by symbol capital E. So the formula for Young's modulus E equal to sigma stress by strain. It is very important for our subjects, our problems. Okay, it is very important formula for our problems. Okay. So this is the final formula for Young's modulus. Similarly, for shear modulus or modulus of rigidity, the definition also same. Within the elastic limit, the shear stress is directly proportional shear strain. That proportionality constant is called shear modulus or modulus of rigidity. So shear stress is directly proportional shear strain. Here the tau is the symbol for shear stress and pi is the symbol for shear strain. Okay, yeah, this is the proportionality constant. This proportionality constant is called shear modulus or modulus of rigidity. Now it is denoted by symbol capital C or capital M or capital G. These three are the symbols for shear modulus. Okay, units are same as stress. Okay, because it is a ratio of stress by strain. Strain has no units, so the units for modulus three elastic ones same as stress. Okay, and last one is bulk modulus. Okay, it is the ratio of direct stress to the volumetric strain is called bulk modulus. Okay, here it is denoted by symbol K. Okay, so the formula for bulk modulus equal to stress, direct stress by volumetric strain. Volumetric strain means change in volume by original volume. Okay, now the last step is the what are the relations between three elastic constants, that is the relation between Young's modulus E and shear modulus CRG and bulk modulus. What is the main relation between these three? The standard formula for the Young's modulus, shear modulus, and bulk modulus is capital E equal to C into 1 plus mu equal to 3k of 1 minus 2 mu equal to 9kc by 3k plus C. Here mu is the Poisson's ratio. Okay, C is the uh, shear modulus. Okay, shear modulus or modulus of rigidity, and capital E is the Young's modulus, and K is the bulk modulus. Okay, this is the relation between three elastic constants. Okay, now in this session, this is a last topic. There is a formulas used in bars of varying cross sections. Right. For solving these type of problems, we need formulas. Already we discussed in previous, but I repeat. Okay, here you can observe here this example having three different diameters, that is D1, D2, D3. That's why for different diameters having different cross sectional areas. So the A1, A2, A3 are the corresponding areas. That is pi by 4. D square is the area of each bar. Okay. Here the load also different. The P1 is the load acting on the bar 1, P2 is the load acting on the bar 2, P3 is the load acting on the bar 3. Okay, so here the stress induced in the bar 1 equal to load acting on the bar 1 by cross section area of the bar 1. So that is P1 by A1 is the formula for stress induced in the bar 1. Okay, so here L1 is the original length. Okay, L2, L3, L1, L2, L3 are the original lengths. Okay, now sigma 2 is the stress induced in the bar 2. That is P2 is the load acting on the bar 2. So P2 by A2 is the formula for stress induced in the bar 2, and sigma 3 is the stress induced in the bar 3. So the load acting on the bar 3 equal to P3. So P3 by A3 is the formula for stress induced in the bar 3. Okay, now already we discussed in previous, there is a strain having, already we know the Young's modulus equal to stress by strain. Okay, from that formula, strain equal to stress by Young's modulus. Okay, so here stress equal to P1 by A1, that is load by area into Young's modulus. So strain in bar 1 equal to P1 by A1 E1 is the formula for strain produced in the bar 1. Similarly, epsilon 2, epsilon 3 is the strains produced in bar 2 and bar 3. Okay, now by using these three stresses and these three strains, we have to calculate total deformation in length. Okay, L1, L2, L3 are the original lengths. and delta L1, delta L2, delta L3. Okay, delta L is the change in length, total change in length. Okay, delta L1 is the change in length in bar 1, delta L2 is the change in length in bar 2, delta L3 is the change in length in bar 3. Okay, this is the formula for change in length. Okay, change in length is obtained from the strain equal to delta L by L. Okay, so delta L equal to strain into original length. So from this formula, these are the individual strains. Okay, if you want to find out the total deformation in the bar, then you have to add all these three values. Okay, total change in length or total deformation in the bar is obtained by adding three deformations: delta L equal to delta L1 plus delta L2 plus delta L3. Okay, this is the final formula for total change in length or total deformation in the body. You have to consider positive sign for tensile loads and negative sign for compressed loads. It is very important. Okay, okay, friends. Okay, thank you.